Hey everybody. Today we're going to work through some very specific types of problems. You can see the title up on the top. We're going to discuss some distance, speed, and time problems for today. I want to go through a couple different ways that you can format a solution to them, and then we'll talk maybe a little bit about some quirky situations that can pop up. Okay, let's jump right in. Take a moment and I want you to read problem 1. Okay, give it a good read. Make sure we understand the context. Okay, pause it now. Okay, so you take a peek at problem 1 and it starts to talk about a distance we've traveled, how long it took us to travel that in two circumstances, and the speed at which we were going. So I want to make sure that we are good with a relationship between distance, speed, and time. Sometimes a little triangle gets taught to discuss that topic. I would rather us just use some logic, okay? If we needed to build a relationship between distance, speed, and time, I hope that it's pretty logical that how far you go, distance, depends on how fast you go and for how long. That just being, my distance equals my speed times my time. How far I go depends on how fast I go and for how long. And if you can remember that purple logically, then I hope that your other stuff just kind of comes from your algebra. Like that is, the conclusion to that could be that if you ever wanted to know what speed was, then you need to divide out your time. Or if you ever needed to know what time was, then you could divide out your speed. And so if we know the purple, then we can always manipulate that to get the red or the blue. So I think it's a really good idea to put that purple down at the top of your page. And then after that, don't write it down again. Try to work through that relationship from a logical standpoint. Okay, if we take a look at that problem, well, the question that we've been asked to find is how many kilometers were traveled over land and water. So for us to answer the problem asked, we need to be able to say, how far do we travel on land? How far do we travel on water? Okay, well, if that's what we're asked to find, then maybe that's what we allow our variables to be. So maybe we have to come up with two variables. And so maybe we say that I'm going to let, x represent the distance on land. And if I do that, then I could say that I'm going to let y represent the distance on water or over water. But maybe we could draw two things together. That is, the problem tells us that there was a total distance of 185 kilometers traveled. And so rather than me using another variable, y, as soon as I say that x is the distance on land, then I know that my distance on water has to be the total minus my land. And so maybe what we can do then is we can write my distance on water in terms of x, and now I don't need two variables. If I don't need two variables, then I don't need to build a system. And maybe that's somewhere that I could go with it. So let's work through on that. Okay, that's what I need to find. X is my distance on land, 185 is my distance over water. Well, now I need to try to build an equation. Okay, the question also tells me that it took me 5.75 hours in total to go over land and water. So I know my total time. Now, if I had to use some subscript, what I could end up saying then is I know that 5.75 would have to equal my time on land plus my time over water. And so I could build an equation like you see in green if I was able to come up with expressions that represent time in both cases, land and water. Well, if I take a look up at the very top of my page, distance equals speed times time, and then if I look down at the blue, that means I know that time has to equal distance divided by speed. Then I could come up with two expressions, an expression for both land and water because I know the speed I traveled on both. So I'm going to use that green, of which I'm about to erase, to build my equation. Okay, I'm using the blue up at the top. I know that my time spent on land, time on land has to be my distance, which was x, divided by my speed, which was 40 kilometers an hour. I have to add to that my time spent going over water. Well, time is distance over speed. And you'll notice both of those speeds are in the same units, kilometers per hour. My distance on top is in kilometers, so all of my units line up. I know then that total time has to be 5.75 hours. And there you go. So I knew the relationship between distance, speed, and time. That allows me to build that equation. Okay, for some of us, we don't like that equation that much because we have fractions. However, I think we should be pretty good to be able to say, if I want to get rid of a divide by 40, then I'm going to multiply by 40. And if I want to get rid of a divide by 10, well, then when I multiply by 40, that will take care of my 10. And so we should be multiplying every single one of those values by 40. And so when we do that, we like that because now our denominators disappear. So that's really nice. So when I work my way through, I can then say, well, then I'm going to have 40 divided by 40. So there's just my x. But my 40 divided by 10 is a 4. So now when I go through and I calculate, well, 4 times 185. So 4 times 100 is 400. 4 times 80 is 320. So there's a 720. And 4 times 5, 740. And then my 40 times my 5.75, well, that's my 200. And then another 30, 230. And now I have a much more manageable equation. I can simplify. Maybe I decide and I say, hey, let's get rid of that plus 740. So I'm going to minus 740. And now I can divide both sides by -3. When I take that 510 and I divide it by 3, well, my 51 divided by 3 is 17. So there's my 170. Okay, what did I just find? Take a look back up in your let statement. I see that x is 170. X represents the distance on land. So I now know what my distance was on land. Now, I do not need to see you go through and then say sub x equals 170 into 185 minus x. You should be fine that once you find x, your next statement, which really is a then statement, you can use that to find your own water. So I do not need to see that substitution within your solution. I think we should be good at the end of the blue to say, therefore, 170 kilometers, put on our units, on land, and now draw your conclusion, 15 kilometers over water. And there would be a way for us to be able to go through and solve that problem. Okay, I would argue that I think that that's a pretty direct way. Look up in the question, what did the question ask for? Allow your variable to represent that, so when you solve the equation, you've found part of your answer. Now, there are a bunch of different ways to be able to solve that problem. Like, I didn't have to build a time equation. I could have used that time to go through and build a distance. There's a bunch of different ways. What I want to talk to you about now is another way to tackle problem 1. And it's just a different way to structure your solution. Really, where I'm coming from is take a look at the top, your let and then statement. If you don't like writing those and then using those to build your equation, then there's a little bit of a structure you could use that could help you out. Okay, let's try problem 1 again. Okay, so what you see up at the top, there's our same problem 1. We don't need to take time reading it. What some people like to do is they like to build a little bit of a chart. And that chart relates to distance, speed, and time. So what I'm going to do, and if you can wait for a moment until I've built the chart in its entirety, I'm going to have distance, speed, and time. Now, I just write down the purple, but I know that is the relationship, that distance equals speed times time. But what those purple titles do, distance, speed, and time, is I use them to build columns. Now, when I see the problem is relating to 2 different circumstances, and my 2 different circumstances are the fact that I have information over land and water, right? Land and water. Then what I can do is I can now construct this extra column that's comparing the 2 situations we're working with. So I'm going to have one circumstance where I'm talking about land, and then I'm going to have another circumstance where I'm talking about water, because each of those situations has its own relationship. Okay, what I actually have in my chart then is a bunch of different ways to build equations. Notice distance equals speed times time. So I could build an equation across if I had land information. I could build an equation across if I have water information. But I could also build distance information, time information. We're going to see something in a moment where I don't really use speed information. Okay, I want to show you what I'm talking about when I say, let's build that chart. I'm just going to shrink that down. Okay, I'm going to plug in everything I know about the specifics of this problem. Okay, my specifics. My speed over land is 40 kilometers an hour. My speed over water is 10 kilometers per hour. Now, if you look at the rest of the information, I don't really have a place to put it. But the reason I don't is because I actually have a third column in there. And what it is, a third row, it's my total row. And if I wanted to now plug in my information into my total row, I know that my total distance was 185, and I know that my total time was 5.75. Now, I do want you to notice, I don't really know what my total speed is. And yes, I could figure it out, but I don't know if it's meaningful. Like, what would it be? Would it be an average speed? Okay, take a look at my 2 columns now that have missing information, my distance and my time. I can start plugging in variables that allow me to build my equation. Okay, watch what happens. And I'm going to first build it to mimic what we did in the last problem. I could now say, hey, I'm going to let my distance on land be x. And you'll notice in the final column, as soon as I make my distance x, and I know that time has to equal distance divided by speed, that my time has to equal distance divided by speed. Well, you take a peek. If my total was 185, then my water has to be 185 minus x. And as soon as I plug that in, then I know that my time has to be 185 minus x over 10. Okay, I'm just going to circle something right now. There's the equation that I used to solve the problem. My time on land plus my time over water has to equal my total. And if you look back at your solution that we wrote down for the first time, there's your equation that you use to solve. Now, that chart that I just set up, that is a completely acceptable way to set up your problem and not write let statements. I think your reader should be able to interpret that chart and see that you called land X. So you have defined your variable. Land, what about the land? The distance. So the distance on land was X, and everything else falls into place. Okay, I'm not going to go through and solve that problem the same way, just because I want to show you variety. For some of us, because we went through and we allowed our X to be our distance on land, that created an equation with fractions in it. Now, it meant I maybe didn't have to do that much work to build my equation. It was logical, but it meant that maybe I needed a little bit more work to eliminate my fraction. I want to show you there's a variety here. And actually, what I'm going to do on this one, I'm going to do it in two variables, just so you can see how you could set this up with a system as well. Okay, let's say that I start off the whole problem by saying, well, I'm going to allow X to be my time on land. Okay, well, I better plug in everything else I knew. I knew that speed was 40 kilometers an hour. That was 10. No such thing as total speed, really. My total distance was 185, and my total time was 5.75. All the orange stuff was given. Well, now look what happens if I allow my time on land to be X. Well, then I know distance equals speed times time. So my distance on land has to be 40x. My speed, 40 kilometers an hour, times my time. Now, if I wanted to go one variable, I could then draw the conclusion that 5.75 minus x has to be my time over water. Which then means, and I'm going to sneak this in as best I can. Let me see if I can blow that up to make it easier. That 10 times 5.75 minus x is my distance on water. Well, you take a peek. You could now build an equation. That 40x, my distance on land, plus my 10 times 5.75 minus x, my distance over water, has to equal my total distance. You can go ahead, you can expand in your 10, you can solve, but I told you I was going to do this in two variables. But you can see an alternate way to work through. Now, the reason why I might not like that way as much is notice when you get down to a solution for x, you didn't answer the question. The question asked how many kilometers were traveled, and what you then found was the time. So that would require you to take that x and instead sub it back in all the way over here to find the distance on land. A little bit extra work. Easier equation to solve, but a little extra work in the end. Okay, I want to walk through then your alternate way to be able to solve. So if I get rid of all that equation stuff, and what I'm going to do is I'm just going to eliminate this single variable option for what we had in time. Okay, if I was to go through and say, you know what, I'm going to make this the least amount of work I do at the beginning. That when I go through and I say time's going to be x, then I'm going to say, you know what, let's let time on water be y. Like no thought. Well then, draw your conclusion. Distance equals speed times time. And now, because you have two variables, that's going to require a system. So I'm going to create two equations. One equation from my time column. My time on land plus my time over water has to be 5.75. There's equation one. But then you'll also notice I can create a distance equation. That my distance on land plus my distance over water has to equal 185. And there's equation 2. Okay, 2 different ways to get there. Now, you'll notice that because we created a system, we put no effort in early, it's going to require extra work now. I would hope that we would just use elimination and maybe multiply equation 1 by 10. That's going to give you a 10x plus a 10y equals 57.5. That's now equation 3, and we should be good to solve that. That if you work your way through, I'm going to now take equation 2 and subtract equation 3 so that I have positive coefficients. When I take my 185 minus my 57.5, that's going to give me 127.5. And now when I divide out my 30, that's going to give me a relatively clean 4.25. Now, what does that x represent? It represents my time on land. Well, here's where I'm going to argue we're just going through a reflex action. If your next action is to say, well, then I'm going to sub x equals 4.25 back into, like now we're just generically solving a system. And if you notice, I never asked you to do that in the problem. We're trying to answer the problem that was asked. So rather than just reflexing into, okay, solve the system, let's actually answer the question we have. So since we found that x equals 4.25, let's go ahead and let's sub it back into my distance that contains x. So my next action then is going to be, I'm going to sub x equals 4.25 back into 40x. That's going to give me my 40 times 4.25. And when I get my 40 times 4.25, that's going to give me my 170 kilometers. And you'll notice that lines up with what we found out before. Now, you could, if you wanted to, solve the system, but then it requires your y value to sub in to get your distance on water. I would argue to you, don't. Now that you know that the distance on land was 170, you know the total was 185, you could then draw your conclusion. Therefore, 170 kilometers on land and 15 kilometers over water. Man, that's pretty sloppy on the bottom. So, 2 different ways to tackle those problems. Now, I know that that was a lot of time spent on those 2 problems, but I think that that chart could be a really nice organizational tool for you to be able to create an equation with speed, distance, time information. That when you have that relationship in the problem, it gives you so many ways to solve that problem. Do you want to use 1 variable? Do you want to use 2? What do you allow your variable to represent? A distance, a speed, or a time? Then, how do you want to structure it and present that as a solution? I think the chart is very useful. I'd recommend it. Okay, so what I want to do now is I want to jump into a couple other speed, distance, time problems, and let's see if we can use the structure of that problem or that solution type to help us out. Okay, let's jump into the next problem. Okay, so let's take a look at problem 2. Take a moment, give it a read, okay? Pause the video now. Okay, we're back. So you've given it a read and you notice we have this 500-kilometer trip. That trip is broken up into highway driving and dirt roads. We've been given speeds on highways and roads. We've then also been given some information about the time. The question asked us in particular, how long did she drive on both? Now, that could be like a really ambiguous, I don't know if you can be really ambiguous. That could be an ambiguous question. Like, what does how long refer to? Is that a distance? Oh, well, she drove on the road for 200 kilometers. Or is it a time? I would argue to you that when I read the question, if her total trip took 6 hours in total, the sentence starts off with a reference to time. How long did she drive on both? I think that long refers to time. So for us to answer this question, you need to tell me what was the amount of time spent driving on a highway, what was the amount of time spent on dirt roads. Okay, to make sure that we are good with that interpretation. Now, what I want you to do, let's try using our chart. So let's build a distance, speed, and time chart. I'm going to build a column for each. Then what I'm going to do is I'm going to break down the comparison. Okay, we're talking about on highways and we're talking about on roads. So maybe I just say, I'm going to use a short form here. There's my highways. But then I also have my dirt roads. And I know that I want to include some total information. There's the setup of my chart. Okay, what I want you to do, take a moment, fill in everything you know from the problem. Okay, pause the video now. Okay, we're back. So hopefully we recognize that we had a total of 500 kilometers. She drove 90 kilometers an hour on highway, 70 kilometers an hour on the roads. Her trip took a total of 6 hours. And I know total speed doesn't, like I don't add 90 plus 70 and say, hey, wow, on total, she was traveling 160 kilometers an hour. No, that's not the way speed works. Good. Okay, if we've got all that, then we interpreted the problem and we were able to plug in some information into some useful spots, into this structure. Okay, the question asks us to find how long did she drive on both. That references to time. So my suggestion to you would be, why don't we let time be our variable? Now, you can pick, do you want X to be your time on the highway? Do you want X to be your time on the road? Do you want to use two variables, X and Y, and solve a system? Okay, your choice. What I want you to do, determine how you want to use your variable, and then I want you to try to fill in the rest of the chart. Okay, pause it now. Okay, we're back. So I am going to be both lazy and efficient. And what I mean by that is I'm going to work like left to right, top down, and I don't want to solve a system if I don't have to. So I'm going to try to solve in one variable. I think if I were to solve this problem, I would make X be my time on the highway. Now, the only reason I say that, I'm going to use one variable, and I'm going to be lazy and go top down. There's nothing that makes me in this problem feel like I need to skip the time on the highway. The problem asked me to solve for time, so I'm going to let my X be that. Okay, what conclusions happen then? Well, if my time on the highway was X, then my time on the road must be 6 minus X. Then, if those are my times, I have my relationship between distance, speed, and time. I know that distance is speed times time. I know that distance is speed times time. Okay, I want to highlight one thing, just to make sure that we fully understand what's happening. I only have one equation I can build. And you may be looking at that going, but wait a second, we had two. We were able to draw two last time. Be very careful. When I zoom in, that relationship is the one that allows me to build an equation. Because in essence, I already used the other equation. Can I get you to focus in on the time column? As soon as I decided to use one variable, I actually used that equation. So I cannot build an equation with time. I'll show you why I can't, but then I'll show you the background to it. If I did, I'm going to try to say, well, X plus 6 minus X equals 6. Time on highways plus time on roads equals total time. Well, my x's cancel out, and I get 6 equals 6, and I should go, okay, that's always true. 6 always equals 6. But that equation didn't help. I actually built an equation that has infinitely many answers. And I'm going to argue to you, of course you did. The way you got 6 minus x for your time on roads was because you used that green equation. Okay, just so you understand why. Had I made time on roads be y, well, then you would have built the equation x plus y equals 6. If you were a system person, you have that equation in your system. But maybe what you would have done is you would have said, hey, I'm going to use substitution. So you would have rearranged that equation, maybe for y, and then sub it back into the other equation. Look what I just built. Y is 6 minus x. Yes, that's how I built it. So just be conscious of, if you use one variable, you're using it depending on the other, you are creating the other expression by depending on that information. And so you can't build another equation within that information and not expect to get an infinitely many answer. Okay, I'm hoping that that makes sense. What I'm going to do now is I'm just going to get rid of all of that mess, and I'm going to go back to what we had talked about. I am going to use my distance now to build my equation. Okay, that allows you to say that my distance on the highway plus my distance on dirt roads has to give me my total distance. Okay, I've built one equation with just an x in it. Now we should be really fast to solve that thing. Okay, if I caught up to you, what I want you to do, pause the video now, get a little bit of proof, a little bit of exercise that you can solve that blue equation. Okay, pause it now. Okay, we're back. So we can go ahead and we can expand in that 70. I'm hoping that we can go ahead and isolate, so we'll simplify our x's, then also get rid of our plus 420. We can then divide out that 20, and we get down to 4. Okay, what did x represent? Well, x is coming all the way back here. X was my time on the highway, so let's draw our conclusion. Therefore, 4 hours on the highway. And if I have a total of 6, or sub it into the other expression, 2 hours on roads. And there we go. Okay, I'm hoping that you like that chart setup. I'm hoping that it gives you a structure that makes it a little bit easier to build an equation out of it. Of course, you could have dealt with that whole thing just using let statements. Okay, let's jump into the next one. Okay, there's our problem 3. A survey crew took a trip up the river and back in 10 hours. Going upstream, they paddled at 4 kilometers an hour, but downstream, they traveled at 12 kilometers an hour. How far upstream did the crew go? So when they were paddling against the current, they went 4 kilometers an hour. But when they traveled with the current was helping them, they were able to travel at 12 kilometers an hour. How far upstream did the crew go? Okay, let's try to use our structure for our chart. So I know I have a relationship between distance, speed, and time. I can build my columns. What am I comparing now in this problem? Well, I'm comparing going up the stream and down the stream. Now, some people might look at that and go like, hey, how about we go up and back? And I go, sure, I don't think it really matters. And I know that I might be talking about totals. Okay, if I leave that structure to you, I want you to do the same thing we did in the last one. Let's go through and fill in everything you can. Okay, pause the video now. Okay, we're coming back. So if I fill in everything, a crew took a trip up the river and back in 10 hours. Now, one mistaken conclusion that you could have drawn is you said, well, hey, if I go up the river and back in 10 hours, then that means I went 5 hours up and I went 5 hours back. And I go, whoa, 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 whoa. Remember, we're going at different speeds. If I'm going up the river, let's assume I'm going against the current. I was only going at 4 kilometers an hour. What that assumption would have made then is that I traveled an equal distance up and back. It's the only way I can return. And so we have to be careful that we don't just cut our our time in half. No. So I know my total time was 10 hours. Going upstream, we could only go as fast as 4 kilometers an hour. Downstream, we could go a lot faster, 12 kilometers an hour. My total speed doesn't matter. How far upstream did the crew go? Okay, well, you'll notice we don't really have a total distance on this one. And here's where I'm going to argue we just need to be careful. Let's start to work our way through. The question said, how far upstream did the crew go? And so if we were to go, hey, how far? That's a distance. Then we may be inclined to say, I'm going to allow up the stream to be X. But some people might not like that because I know my relationship between distance, speed, and time. Distance equals speed times time, so time equals distance over speed, and you may not like the fact that you have a fraction in there. So if that is something that you do not like, then I'm going to argue to you, don't let X be your distance. Let X be your time. Yes, it means it's going to take a little bit more work when we finish off the problem because X does not represent what you've been asked to find, but maybe the equation you build is so much easier that your risk for mistake is less. It's a better strategy. Because now if I let time be X, then my distance is 4X. Okay, well, if my total time was 10, then I know that my time coming back has to be 10 minus X, which means that my distance coming back, I really need to make these spots bigger, has to be 12. You know what? I'm just going to blow it up. 12 times 10 minus X, and there we go. Okay, we used up our time because we wanted to use one variable, but we take a look. I wish I knew the total distance. And I'm going to argue to you, it doesn't really matter. Now, I do recognize that this takes some interpretation, and maybe this is a little ambiguous, but I'm going to clarify some wording in the problem. It says that a survey crew took a trip up the river and back. And I would make the argument that up the river and back infers that wherever your start was, you went up the river, but then you came back to the same spot. Not to a different spot. You didn't stop short. You didn't go longer. No, wherever you entered that river, you came back to that same spot. I realize I'm inferring that, but I hope that that's a pretty safe assumption. If that's the case, then we should be good that whatever distance I traveled up the stream, I had to travel the exact same distance back. So therefore, my distance going upstream has to equal my distance coming downstream. And that's what allows me to build that equation. So I don't need the total distance. In fact, I don't really care what the total distance is. I just know they have to be equal. Okay, that creates a super easy equation We're probably expanding our brackets, isolating for x. Now, I need to take my 120 and I need to divide that by 16. And that is going to give me a value of 7.5. So what does that x of 7.5 represent? Well, if I go back to my table, that is telling me that x was my time. The question asked me how far. That means I need a distance. So now I'm going to take that x and I'm going to sub it back into my distance expression. So I'm going to sub x equals 7.5 back into my 4x expression. And when I do that, I'm now going to get my 4 times my 7.5, and that is going to give me 30. Now, you just make sure that you put on your units, and that is 30, and we are talking about kilometers. There we go. Okay, so really I went through that problem. I wanted you to be able to build some stuff, get another chance to practice our chart, but also to make sure that if you encounter a problem like this again in the future, you can make that inference, that assumption. If I'm traveling to somewhere and back from that spot, then I have traveled the same distance. Okay, one more problem to go through. Here we go. Okay, I want you to take a read of problem 4. Okay, give it a read. Pause it now. Okay, we're coming back. So when we start to work our way through this one, I'm going to argue to you that I think this one might be the most complex one that we deal with. I don't think it's complex from the standpoint of the algebra. I don't even think it's complex from the standpoint of the concepts in the problem. But what it might be is just a general understanding of what we're talking about when we say that certain objects could have a speed that it runs at, but then the total speed that it actually runs at could be influenced by other things. Now, we're talking about a jet, and it's a jet flying through the air, but that jet's speed is going to be impacted by two things. What's the speed that the jet is set to fly at, right? Like, I realize that a jet doesn't have a gas pedal, but however I was to push down on that gas pedal would drive the plane at a certain speed. So let's call that the throttle. Whatever I set the throttle at for my plane would drive that plane at a certain speed. But then that plane is also impacted by the wind. So if I was to go through and say, I'm going to now show off my exemplary, I don't know, there's my very crude picture of a plane. Here, I'll even give it its front window. There you go. There's my plane. If I was to sit there and say that plane is set by its throttle to travel at a certain speed, then I could use like a symbol for that. And let me just say, I'm going to call that like T for throttle. Okay, let's just say that I'm doing that. I have programmed my plane to fly at a certain speed. Well, if the wind is coming into the face of that plane, then it's going to slow down the plane from what the throttle has been set at. That its actual speed, I might call that airspeed, its actual speed is slowed by the wind. Now, if that wind is rowing at a different direction, well, now that wind is going to help push that plane to go faster than what the throttle was set. Okay, this is very similar to the previous problem of us talking about a stream. I can row my boat. Imagine I'm canoeing, paddling. I can paddle my boat at a certain speed by moving my arms at a speed. But then the stream, the current, is going to push me to go faster or push against me to go slower. The same thing happens when we're traveling by a plane up in the air. So when the question asks, and sorry, I'm going to get rid of my beautiful plane here, but when the question asks, find the speed of the jet and then find the speed of the wind, what it's asking out, what's the throttle speed, the speed of the jet, and then what's the wind speed that's affecting it? Okay, now that we maybe understand a little bit of the context, let's jump into solving it. So if I use that same setup, distance, speed, time, I'll give myself a little bit more space this time, then what am I talking about comparing? Well, it's talking about going on a trip and then returning. So maybe I'm in the same sort of situation as about like I went upstream and then I came back. So maybe I went to my destination and then I came back from my destination. And maybe that's my chart. Okay, I know that I can use some total information from time to time. Okay, let's plug in everything we know. Well, we know that the total trip had a distance of 2,080 kilometers. Find the speed of the jet. Okay, well, we know that the jet traveled with the wind. Okay, well, my chart now doesn't explain with versus against. I do have with and returned. So I do notice then that to and returned have different times. And the time that I returned was the time that took me longer. Okay, so then I was flying against the wind. Well, maybe it's better for me to create my chart in reference to the wind. That maybe I say I'm traveling with the wind and against the wind. And that might be a more explicit way to write that. Because now I can plug in my time and I could say 2 hours and then I could say 2 hours and 10. Oh, wait a second. Now I'm writing in two different units. Okay, I don't want to do that. I want to keep everything in terms of the same units. So I have a choice. I could change them both into hours or change them both into minutes. Well, I don't think I want to change 2 hours and 10 minutes into hours because that's going to require a fraction. So maybe instead what I'll do is I'll change both of them into the smallest units possible. That way I get to avoid the fractions. 2 hours is 120 minutes. So 2 hours and 10 minutes has to be the 120 plus the other 10, 130 minutes. Okay, so I have that. Now, I'm drawing the conclusion of saying 250 minutes, but I don't know if that was even worthwhile for me to put in. It doesn't allow me to build an equation. Notice there is no variable in that column. But by all means, you could fill it in. Okay, the total trip is this. Find the speed of the jet, speed of the... Okay, well, I can infer a couple other things. Everything we just talked about, if I travel to somewhere and back, that means those distances are the same. Which means that I know I went 1,040 kilometers in one direction and 1,040 kilometers back. Okay, that's good. But I don't have the speeds. And we may be tempted to go like, oh, okay, so like make X, and then if I want to use two variables, I can call that Y, and there we go. And I stop for a second, stop. Look at what you just plugged into the table. I just said the speed with the wind was X, and the speed against the wind was Y, but notice neither of those are what the question asked me for. They asked me for the speed of the jet and the speed of the wind. So I am not going to go through and fill in either of those with just an X or a Y. Really what I might do then is I might combine both my structures. I need to clarify to my reader that what I'm going to do is I'm going to let, I don't know, let's go J so that we can represent it as jet. We won't forget. Let J be the speed of the jet. And then I can say that I'm going to let W maybe, to keep the same pattern, be the speed of the wind. Because if I do that, now I can fill in my chart. If I'm traveling with the wind, then that wind is behind me, behind the jet, and it is pushing it to go faster, which means that my speed is going to be the speed that I set the jet at plus the extra speed of the wind. If I'm going against the wind, then whatever I set my throttle at, the speed of the jet, I'm going to be slowed by the speed of the wind now. So I need to subtract it. And I can end up doing that within my chart, and maybe you can see a blending of the two. Now, how can we build some equations? You take a peek. Since you have two variables, it's going to require two equations, but we have a relationship between distance, speed, and time. So now I can go across within my table and I can build those. You will notice that everything that I filled in working across from each other was independent of each other. So I didn't use the time and the speed to create the distance, or I didn't use the distance and the speed to create the time. Since they're independent, then I can build my equation from them. And I could then say, well, then therefore, my distance with the wind has to equal speed times time. And you'll notice that I just put my time first because proper form would have the monomial out in front. That is now equation 1. I could also build a second equation traveling against the wind. Okay, you take a peek at both those equations, and I don't know if those are in the easiest forms for you to use. My suggestion to you, we're going to have to solve a system. Why don't we simplify the system first? I'm going to take equation 1, and I'm going to expand all my brackets. Now, I am going to take a quick look, like a very quick look, and see, could I divide out my 120 right now and simplify my equation? If I take 1,040 and I divide it by 120, I'm going to check and see, do I get an integer? If I do, then I'm going to divide out that 120 in equation 1. If I don't, then I'm going to get a fraction, and I don't want to put fractions in my equation. So when I calculate that, I notice I do not get an integer, so I'm going to expand in my 120. Now I'm going to do the same thing in the next equation. I'm going to see, can I divide out my 130 and get an integer? And I notice I do. When I divide out that 130 goes into 1,040 exactly 8 times. Nice. That means that I don't have to expand in my 130, blow up my numbers and make them bigger. There's my equation 1 and my equation 2. And that's going to be the system that I'm going to work with to solve. Okay, I want to leave that with you. We'll come back and we'll check our mechanics. Okay, pause the video now. Okay, we're back. So, hopefully in that scenario, you're taking a look to try to match up with equation 1. I would have had a bunch of people that would have isolated something in equation 2 and subbed back into equation 1. I would love it, though, if instead we just said, I don't know, I'm going to multiply that by 120, because that'll put the same number out in front of my J or my W. And so if I do that, then my equation 3 is going to become 8 times 120, so that's going to be a 960, is equal to 120J minus 120W. And now I have equation 1 and 3, and I can use elimination. So within that context, I'm just coming up to the right. I'm going to take, I don't know, let's say equation 1, and I'm going to add it to equation 3. I'm going to add it. That way I don't have to deal with any sign issues. So when I do that, then I'm going to get my 960 plus my 1040. That's going to give me an even 2,000. When I add them, then I'm going to get 240J. And when I add them, I'm going to eliminate my W's. So I now need to take 2,000 and divide it by 240, and I'm going to get, an ugly decimal. So I'm going to now divide it and reduce. So at the very least, I can see I could divide by 10. Maybe then you slow roll it. I don't know. Do you take your 200 and over 24 and divide it by 2? If you take your 200 and you divide it at least by 4, then maybe you can jump a little bit. Do you take your 200 and you divide it by 8? If we do that, we can reduce our J right down to 25 over 3. And now we just need to be very, very focused on what units we're going to put on that speed of the jet. Okay, the problem isn't finished yet, though, because we still have to come up with what is the speed of the wind, and that's going to require us to fully solve the system. So what I am going to do is I'm then going to take that J value, and I'm going to sub J equals 25 thirds back into probably equation 2. That one is pretty simplified. And so if I get my 8 equals 25 thirds minus W, then my W is going to equal 25 thirds minus 8, so that would be 24 thirds. That gives me 1/3 as an answer. Now, you could sit there and give me, I'm really making this small, you could give me your solution to this problem as therefore the speed of the jet is 25 thirds, focusing on your units. What units were we talking about? Well, we had kilometers per, and before you write down hours, remember, we changed those times into minutes. So that's kilometers per minute. Now, I might argue to you, I don't know if that makes a whole lot of sense to you. That is, can you estimate? Is that going fast? Is that going slow? I don't. So my argument to you might end up being then, well, let's write it as a decimal so we can talk about it properly. You have your exact answer in your solution. But to be able to talk about that then, you could say the speed of the jet is 25 divided by 3 is 8.3 repeated kilometers per minute. And that might make more sense to you. You could then say that the speed of the wind is 1/3 or 0.3 repeated kilometers per minute. There we go. Okay, that one was a bit of a doozy. Us just getting an idea of what happens when we're traveling with a current against or with the wind and against. Okay, I've thrown a number of problems at you. I hope you like the chart as a setup method, a structure for being able to create an algebraic solution to the problem. Okay, in your solutions, you either need to give me let statements or the chart. Both are acceptable for communicating your solution. They are necessary. Now your job, jump in and get some practice. Make this as automatic as possible. Okay, best of luck.